What is up, YouTube? My name's Hunter, and today we're going to be talking about the principles of flight. I don't know about you, but I find it super fascinating that big airliner jets like the 747 that weigh several hundred tons can fly through the air. Today we're going to be talking about how that's possible and kind of the science behind how this phenomenon happens. As we understand the science of how an airplane flies and why it does the things that it does, we will become better pilots. Alright, so in this YouTube video, we're going to be talking about the 5 main things that make up this lesson of principles of flight. These will include the following: airfoil design and characteristics, airplane stability and controllability, left turning tendencies, load factor, and wingtip vortices. The first thing I want to talk about as related to principles of flight are the 4 fundamental forces of flight which allow the airplane to fly through the air. Thrust is the forward force which propels the airplane through the air. Lift is the upward force created by the effect of airflow as it passes over and under the wing. Drag opposes thrust and is the backward or retarding force which limits the speed of the airplane. And weight opposes lift and is caused by the downward pull of gravity. Now let's talk about what is an airfoil and the terms associated with it. An airfoil is designed to obtain reaction from the air moving over the surface. The reason why we have airfoils on the airplane is in order to create lift. Camber is the curvature of the upper and lower surface of the airfoil. Some other important aspects to know about the airfoil are the leading edge, trailing edge, and mean camber line. And the mean camber line, that is the average of the curvature between both the upper and lower surfaces. Because of the design characteristics of the airfoil, the air traveling over the upper surface of the wing is moving faster than the air that's traveling below. Because of this, there is a change in pressure and a difference in pressure between the air that is below the wing and above. This creates a lower pressure above the wing surface and a higher pressure below. Because of this pressure difference, we know that high pressure likes to go to low pressure. The reason why there is a low pressure on the upper surface of the airfoil is due to 2 reasons. First, Bernoulli's principle. Bernoulli's principle basically states that increased speed on the upper surface of the airfoil will cause a decrease in pressure. Second is Newton's third law. For every action, there's an equal and opposite reaction. Because of this, the air flowing beneath the wing is deflected downward when it hits the bottom of the wing. Because of the opposite and equal reaction will cause the wing to lift. Understanding these basic elements are essential to flight, and I find them super fascinating, and I hope that you find them interesting as well. Moving on to stability and controllability, we'll first talk about stability. Stability is the airplane's inherent ability to recover from any conditions that may disturb its equilibrium. Stability is primarily a design characteristic. In essence, the more stability you have, the more easy the airplane is to control. But too much stability may make it difficult to maneuver. There are 2 types of stability. There is static and dynamic. Static is the initial reaction of the airplane. For both static and dynamic stability, there are 3 different levels of stability. There's positive, negative, and neutral. For static, positive stability, it is the airplane's initial reaction to recover back to equilibrium or straight level flight. For negative static stability, it is the airplane's initial reaction to go away from the equilibrium or straight level flight. Neutral static stability is the tendency to remain in the airplane's new condition. Now talking about dynamic stability, like we said, there's positive, negative, and neutral. Positive dynamic stability is the characteristic of wanting to return back to equilibrium or straight and level flight. Negative dynamic stability is the characteristic of the plane becoming more severe and oscillating farther away from equilibrium. Neutral dynamic stability is the tendency of the airplane to remain the same. The reason why stability is important to us is that it affects us in two main ways: maneuverability and controllability. Maneuverability is the quality of the aircraft that permits it to be maneuvered easily and also to withstand pressures that are imposed while completing different maneuvers. Now, talking about controllability, controllability is how responsive the airplane is to the pilot's inputs. Dynamic and static stability is about the lateral axis, which is also referred to as longitudinal stability. While talking about stability, it's also important to note lateral stability, which is along the longitudinal axis of the airplane. The three main things you need to know about lateral stability are heel effect, swept-back wing angles, and dihedral effect. First, let's talk about dihedral effect. Dihedral effect is due to the characteristic of the wing design, which tilts the wings upward slightly. This is conducive to lateral stability because when a gust of wind rolls the airplane, because of dihedral effect, the airplane will begin to side slip. When the airplane side slips, the lower wing will have a greater angle of attack, resulting in increased lift compared to the opposite wing. This will allow the plane to return to equilibrium. Now let's talk about swept-back angles. Swept-back is an angle at which the wings are slanted rearward from the root tip. When a swept wing airplane is side slipping, the wing toward the side slip will experience a greater volume of airflow over the lower wing than on the wing away from the side slip. This will allow the lower wing to increase lift and return the plane to straight and level flight. Heel effect depends on the action between the relative wind and the side of the fuselage. When an airplane slips to one side, the weight and pressure of the air flowing into the fuselage will push the airplane back to equilibrium. So these three main components are key to lateral stability. All right, now let's move on to our left turning tendencies. So there are 4 types of left turning tendencies. So there is P factor, torque effect, spiral slipstream, and gyroscopic precession. Most people just think of P factor when it comes to left turning tendencies, but as we can see, there are a couple more that we need to understand. Starting out with P factor is due to the propeller, as the descending blade will take a bigger bite of air or have more force than the ascending blade, causing the plane to yaw to the left. Torque effect also has to do with the propeller and engine, as looking from the cockpit from the pilot's perspective, the propeller is rotating clockwise. Because of Newton's third law, we understand that for every force, there's an equal and opposite reaction. Because of the propeller spinning clockwise, the opposite reaction would be to bank to the left. So because of torque effect, this will cause our plane to bank to the left. Talking about spiral slipstream now, spiral slipstream occurs because of prop wash. So as the air flowing behind the propeller, it will spiral around the fuselage and hit the left side of the rudder, causing the airplane to yaw to the left. Gyroscopic precession is when a force is applied, it is felt 90 degrees ahead of where the force was applied. In general aviation, this mostly occurs in tailwheel aircraft. This is because As a tailwheel aircraft is going to lift off and depart on a runway, the tail is lifted upward, causing force to be applied at the top of the propeller, which is then felt 90 degrees from that force, as we just learned, causing the airplane to yaw to the left. Gyroscopic precession can be difficult to understand. I like to think of tetherball. When you're hitting a tetherball, when you first initially hit it, it's not going to go straight up in the air, but it is going to gradually ascend, and about 90 degrees from where you hit the ball, it will feel that force. All right, moving on to load factor. Load factor is the ratio between the total air load acting on the airplane compared to the total weight of the airplane. Load factor is measured in the form of G's, which is the acceleration of gravity, and G's are both negative and positive. I'll give you a couple of examples of what positive and negative G's are. For example, pulling back on the stick or yoke and getting pushed into your seat, that is positive G's. Negative G's would be felt if you push the stick or yoke forward, which would lift you out of your seat. The last topic we'll be talking about today is wingtip vortices. Wingtip vortices occur because of the difference between air pressures that are above and below the wing. Like we talked about before, there is a lower pressure above the wing and a higher pressure below. Since we know that air always goes from high pressure to low pressure, we see that the high pressure below the wing surface is going to flow outward and upward to the lower pressure. The reason why it goes outward is because the air likes to travel with the least resistance, and that is found at the wingtips. The wingtips is where this air will combine from high pressure to low pressure, and thus causing the wingtip vortices. Wingtip vortices are the strongest at high angles of attack, especially when planes are heavy, clean, and slow. The reason why we want to avoid flying through the wake of another airplane's wingtip vortices is because it can cause structural damage and also an induced roll and making the airplane uncontrollable. We can avoid this wake turbulence by staying above the aircraft as we're departing and landing beyond the aircraft and its touchdown point when we are landing. I hope you guys enjoyed the video on the principles of flight as we covered the airfoil design and characteristics, airplane stability and controllability, left turning tendencies, load factor, and wingtip vortices.